Hello, I welcome you all in this course on steam and gas power systems. Today we shall start with the steam turbines. Steam turbines are a sort of prime movers which are used to convert heat energy into the work. If you look at the Rankine cycle on temperature entropy diagram, state 1 to state 2 and state 2 to 3, 3 to 4 and 4 to 1. Now, in this diagram, this isentropic expansion of steam takes place inside a steam turbine. In fact, it was a consistent effort during 18th to 19th century and it started in 17th century to convert heat into the useful work. And steam engine was the first device which was used to convert heat into the useful work. And if we depict the cycle in a steam engine on a PV diagram, it is going to be like this: steam admitting the steam engine because steam engine works on slider crank mechanism like petrol engine or diesel engine. So, it has a cylinder and cylinder is fitted with a piston, and a unique thing here is a piston rod which this petrol engine and diesel engine do not have, that is a piston rod. So, it is fixed with the piston and the piston rod is connected to the the connecting rod, and connecting rod connects the piston rod to the crankshaft which rotates with a certain RPM. So, reciprocating motion of the piston is converted to rotary motion with this mechanism, as in the case of petrol and diesel engines as well. Here this piston rod is taken because the length of the stroke is quite large in a steam engine. If you compare the length of the stroke in a petrol or diesel engine, it is quite large. So, if you do not use this piston rod, then it will obstruct the movement of this connecting rod. That is why a short piston rod is provided in a steam engine, and there are other advantages of having a piston rod. So, if we transform this process of power development on PV diagram, the diagram is going to be like this: 1, 2, 3 in an ideal case. It means the steam is admitting the cylinder, here cutoff of steam supply takes place at a certain pressure, then steam expands in the steam engine up to the state 2, and again it comes back to state 3 through condensation, or it is expelled to the surroundings. If you look at this point, because this curve almost follow the process PV is equal to C. So, this curve tends to be flatter at the end, and if you look at this end, this stroke, the power or the useful work gained during this stroke is not very significant. So, normally instead of expelling steam at atmospheric pressure, at a certain pressure higher than the atmospheric pressure, the steam is extended to the surroundings, so that the size of the stroke or the size of the cylinder is restricted at the sacrifice of a very insignificant power developed during this stroke. Now, if you want to have, because in this case we have not taken the clearance volume into the picture, because if for an actual engine to work, there has to be clearance between the piston and the cylinder head. So, some clearance is provided. In that case, the diagram is going to be modified like this. So, it is going to be 1, 2, 3, 4, 5 and 6. Now, in the steam engine, in fact, the pressure energy of the steam is converted into the useful work. Now, we will discuss about the turbines. In turbines, the dynamic action of steam causes the work. Here in this case, the pressure of steam which is exerted on the piston, which is used for coming the inertia and the friction, is used for developing the work through this slider crank mechanism. In case of a steam turbine, now we have discussed the steam engine, let us come to the steam turbine. Now in case of a steam turbine, there is a dynamic action of the steam. Dynamic action means there is a change in momentum. If we change in the momentum of the steam, right, and the rate of changing of this momentum of a steam will exert force. It is from the second law of Newton's second law of motion. Now suppose we take a plate or curved plate, right, and steam strikes with a certain velocity to this plate. Not strikes, it glides over the blade. It does not strike, but it glides over the blade and leave from the other side of the blade with certain velocity. Let us say velocity V1, it is coming to the blade, gliding over the surface of the blade. This is the blade surface. This is a cross section of the blade. So there is no confusion. Okay, and it leaves with the velocity V2 from the other side. Right, because there is a change in the direction of the velocity, momentum will be, there is going to be a change in the momentum, and this change in momentum will exert force on the blade. But blade is not moving. We have considered that the blade is fixed, but certain amount of force will be exerted on this curved plate or blade. Now in second case, suppose this curved plate is moving with a certain velocity u. Initially, the magnitude of V1 is going to be the magnitude of V2 when u is equal to 0. But now the blade is also moving with certain velocity. In that case, V2 is going to be less than V1. But we will get certain amount of work because force is being exerted, and if we multiply it force with the velocity, that is the amount of work we are going to get, right? Or that is amount of output we are going to get. Now we keep on increasing the value of u. The force, the work will keep on increasing. Suppose V1 becomes equal to u. In that case, there is not going to be any output. So output is 0 when u is equal to 0. Output is 0 when u is equal to V1. Right? Now if we draw a characteristic curve between force and the velocity. Now this is u or u by V1 and this is force. So u by V1, when it is 0, the force is maximum, and when this is equal to 1, then force is 0. So this is going to be like this. But output, because we are concerned, we are not concerned with the force, we are concerned with the output of the turbine. So when the u and V1 will increase, initially the output, that is work, will increase, will attain certain maximum value, and then it will reduce. So at maximum output or maximum work, force may not be maximum. So this ratio is equal to 0.5. This we will discuss later on in subsequent lectures. Now we will start with advantages of a steam turbine over, advantages of a steam turbine over steam engine. Advantage of steam turbine. Now in steam turbine, what happens? There is a rotor. I should explain you the basic working of the steam turbine. In steam turbine, there is a rotor, right? And over a rotor, there are number of blades in this direction. There are number of blades. So there is a rotor. There is a rotor, right? On the rotor, there are number of blades. There are number of blades fixed on the turbine surface, axially as well as circumferentially. So there is a circumferential arrangement of the blades like this. They are curved blades fixed at a different at a certain pitch over the circumference and along the axis of the turbine, right? When the steam glides over these blades, right? When steam glides over these blades, a force is exerted in this direction, and these blades starts moving like this in a rotational manner, and that is how the RPMs are imparted to the rotor, and the rotor is connected to the generator, and that is how the electricity is generated. Now, advantages of steam turbines are, first of all, there is no reciprocating mass. Steam turbines are rotary machines, so there is no reciprocating mass, or there is no linkage to convert reciprocating motion to rotary motion as in the case of steam engine. So there is no unbalanced force in steam turbines. So balancing is not a problem. Second thing is wear and tear is less. Wear and tear is less, and we can directly couple the steam turbine shaft to the generator. There is another thing, there is no sliding member. In reciprocating system, there are sliding members which causes losses due to friction. So here in the steam turbine, there is no sliding member. Third thing is the speed. In reciprocating engine, the limiting speed is approximately it is 300 RPM. It's very low. But if you compare this with the steam turbine speed in the steam turbine, in a single stage steam turbine, we can go up to 40,000 RPM. But 40,000 RPM is not very useful for us if it is directly available. We have to reduce it to 3,000 RPM, because our generator sets or the electricity generators, they work on 3,000 RPM. How it is reduced from 40,000 to 3,000, we will discuss later on. It is not appropriate to discuss it here. In the steam turbine, lubrication, internal lubrication is not required. In reciprocating engines, the lubrication is required. In the steam turbine, internal lubrication is not required. Though some hydrodynamic bearings or different type of bearings are required for to support the rotating shaft, but not much lubrication is required in a steam turbine. And the most important thing is efficiency. Efficiency of steam turbine is approximately 60%. Efficiency of steam engine, maximum efficiency can go up to 20%, otherwise it is 15 to 20%. So efficiency of the steam turbine is quite high. Third thing is, in steam engines, the steam is sent to the surroundings, or if you have seen in the PV diagram, even the exhaust valve is opened above the atmospheric pressure. If you look at the PV diagram, steam engine, the exhaust is opened slightly above the atmospheric pressure. Right? But in the case of steam turbines, when you draw the temperature entropy diagram for the steam turbine, the steam can expand pressure below the atmospheric pressure, and normally pressure in the condenser is approximately 0.1 bar, 0.1 to 0.2 bar, and output of the turbine depends upon output of the turbine depends upon H1 minus H2. So definitely higher vacuum we are maintaining here, more output we are getting from the turbine. However, in the case of steam engine, we are sending steam out to outside atmosphere at a pressure slightly above than the atmospheric pressure. Definitely we are drawing more energy from the same amount of level energy at state 1 in the case of steam turbine. So, and last but not the least, they are suitable for the generator because output is in form of rotary motion, and so it can be directly coupled to the generators. Now, The second thing, these are the advantages of steam turbines. Now we will go for the classification of steam turbines. Classification of steam turbines. Now for the classification of steam turbines, mainly there are two types of turbines, impulse turbines and impulse reaction turbines. Now impulse turbines, in impulse turbines, the steam, high velocity steam which is coming from the nozzle. Actually what happens, the steam available in the boiler which is coming from the boiler, it passes through a nozzle. Right. So, this high pressure steam, the energy or enthalpy of this high pressure steam, part of this enthalpy is converted into the kinetic energy, right, and this high velocity steam glides over the blade surface, and that is how the output is generated in a steam turbine, or the power is generated in a steam turbine, right. Pressure drop takes place only in the nozzle. In impulse turbine, there is no pressure drop during this passage, pressure remains constant, right, and the output is by virtue of only change in the rate of change of momentum. So, this type of turbine is known as impulse turbine. Now, second is reaction turbine or impulse reaction turbine, because pure reaction turbine is not practical. So, we take impulse reaction turbine. Now, in impulse reaction turbine, the pressure drop takes place in this passage as well. So, in impulse reaction turbine, the pressure drop takes place inside the nozzle and inside the and through the blade passage as well, and combined effect of these pressure drops exerts pressure on the blades, and that is how the power is generated. Now, the second is this on the basis of direction of flow. Most of the turbines are axial flow turbines. Now, axial flow turbines means there is a rotor and the direction of the flow of steam in the axis of the rotor. Blades are fixed circumferentially and axially as well, okay, and steam glides over the blades and it exerts pressure tangential to the rotor, and that is how the rotor starts moving. So, these type of turbines are known as axial flow turbines. There are radial flow turbines also. Axial, radial. Now, in radial turbine, the movement of the steam is in the radial direction, and the most very popular turbine is a radial turbine is Ljungström turbine. Ljungström turbine. In this turbine, there is a grid of moving blades in opposite directions, and when the steam flow in the radial direction, the output is produced, right. There are tangential flow turbines also. Tangential flow means the steam strikes the blade in the tangential direction, but steam turbines are rarely tangential type of turbines. In some of the applications they are used for running the auxiliaries, for small capacity power generation or for running the auxiliaries in the power plants, they can be used, but normally most of the turbines are axial flow turbines. Now, another classification is means of heat supply. By how the heat is supplied, means of heat supplied. Now, in a turbine is denoted like a diverging passage like this. This is high pressure side and this is low pressure side, right. So, one is single pressure turbine. Single pressure turbine means steam is entering from 1 and leaving at 2, that is single pressure turbine. Mixed or dual pressure turbine. In mixed pressure turbine, at some intermediate space there is also an entry of the steam, that is, I mean, instead of having entry at one pressure, the entry of steam is at different pressures. So this is known as mixed or dual pressure turbine. And as we discussed earlier also, there is a reheating arrangement also in the turbines. In reheating arrangement, the steam entering the turbine is taken at certain point, heated, and then it is resent to the turbine for expansion. So this is a reheating. Reheating we have amply discussed, reheating and regeneration. In case of regeneration, the feed water is heated with the help of exhaust of the turbine. So that is a regenerative arrangement in the turbine. Now another classification of the turbine can be on the basis of heat rejected. How the heat is rejected from the turbine. The first is pass out turbine or extraction, both are same. Pass out or extraction turbine. Now in pass out or extraction turbine, during expansion in the turbine, starting from state 1 and this is state 2, at some intermediate place the steam is tapped and steam is used for some chemical process or some process in the industry. So this type of turbine is known as this type of heat rejection is turbine having this type of heat rejection system is known as pass out or extraction turbine. Regenerative turbine we have discussed in earlier lectures. What is regeneration? Condensing turbines is a normal type of turbine where condensation of fluid takes place. I mean there is a condenser, turbine, condenser, pump and boiler is normal arrangement, that is known as condensing turbine because steam gets condensed in a condenser. Now non-condensing turbine, I mean the steam is sent to the surroundings. So steam does not get condensed in the closed cycle, so that is non-condensing turbine. Back pressure or topping turbine. Now in back pressure, the steam coming out of the steam is extended up to the lowest possible pressure, and this steam coming from the turbine is used for at the exit of the turbine, not at the intermediate state, but at the exit of the turbine is used for some industrial process. For example, in sugar industries, the power is generated and the exhaust of the turbine, the steam is available at very low pressure and temperature. This low temperature, low pressure steam is used for processes in the sugarcane industries. Now number of cylinders is turbine, say the expansion of steam need not take place in a single entity, it can take place in different turbines. Okay. So in a power plant normally there is a high pressure turbine, it has intermediate pressure turbines and it has low pressure turbines. The power plant can have 2-3 low pressure turbines, 2-3 intermediate pressure turbines. They are known as IP, IP1, IP2, IP3, LP1, LP2, LP3. Normally it is considered when the inlet pressure in the turbine is 5 bar or less than 5 bar or 500 kilowatt. The pressure is less than or equal to 500 kilopascal, then it is known as low pressure turbine. And by visual inspection you can judge which is high pressure turbine, which is low pressure turbine, because high pressure turbine the specific volume of the steam is less, so it is going to be smaller in size. As the pressure of the steam reduces, specific volume of the steam increases, and that is how the size of the turbine keeps on increasing. They can be tandem turbine. There is another classification. Tandem means output is coming to the common shaft, right? Or there is a tandem type of arrangement and there is a cross compound type of arrangement where output from each turbine is sent to an individual shaft. So that is known as cross compound type of arrangement. The turbine can be a single flow or double flow type of turbine. Single flow means steam is entering from one side and leaving from another side. This is single flow. Double flow, normally double flow arrangement is done in low pressure turbines because the size of the low pressure turbine is big, they are bigger in size. So, in that case steam enters in the middle and it moves axially in both the directions, right. So, these two type of arrangements, inlet steam arrangements are also possible in steam turbine. Now, there is another classification because that is based on a rotational speed. Now, rotational speed of a turbine, here we supply 50 hertz, our electricity supply is 50 hertz. In some of the countries like it is 60 hertz, some of the countries it is 75 hertz. Now, we will focus on this 50 hertz. Now, for 50 hertz supply, if you want to have 50 hertz supply, then RPM of the motor is going to be 120 F by P. P is number of poles. Because if you go to the market, you will not find motors for all RPMs. You will find motors for 3000 RPM. Like for example, your this small capacity generator, petrol running with the petrol. This of capacity 1 kilowatt or 1.5 kilowatt, you will find it is running at 3000 RPM, or you will find machines running on 1500 RPM, or you will find machines running on 7500 RPM, sorry 750 RPM, right. So, in market the electrical machines are not available for all RPMs. There are certain RPMs, only for those RPMs you will get the machines. Now, how these RPMs are decided? Suppose I take 2 poles motor. Now, sorry, 2 poles, if I take 2 poles, P is equal to 2, F is 50 hertz, it is fixed, right. So, N is going to be 120 into 50 divided by 2. So, it is going to be how much? This 60 into 50 is equal to 3000 RPM. Suppose we can go for 4 poles also. If we go for 4 poles, this will be reduced to 1500 RPMs. If we go for 8 poles, this will be reduced to 750 RPMs, right. Now, I want to have output of 60 hertz. Now, 60 hertz output, now again we will use the same formula, N is equal to 120 F by P. So, if F is equal to 60, 120 into 60 divided by 2, it is going to be 3600 RPM. In some of the countries, this electricity supply is 60 hertz. So, 360 RPM again, if we go for 4 pole, then it is going to be 1800 RPM, and similarly if we go for the 8 poles, it is going to be 900 RPM. I think this is all for the classification of steams, right? Sorry, classification of steam turbine. In the next class, we will start with the compounding of steam turbine. Thank you.